Everything we do is available freely on bionichaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Ever wish you could just design a brain, not just daydream about it, but actually dial up a specific brain state? Super focused or maybe totally relaxed. Well, today we're sort of peeling back the scalp, metaphorically speaking, to look at a technology that lets you do pretty much that. And as we'll find out, it's way more profound and actually, funnily enough, far messier than just some kind of mad science experiment. So our mission for this deep dive, it's pretty clear. We're exploring the world of EEG, that's electroencephalography. And specifically, this really clever bit of tech that creates synthetic brain signals, fake ones. We'll get into why anyone would even want to generate artificial brain waves, what makes them surprisingly real, and what they tell us about the super complex and, often very messy signals our actual brains pump out. We're given the fluff, jumping right in.
Yeah, and what's really fascinating here is how these digital copies actually help us figure out the real thing. It's like building this controlled, almost sterile environment so we can understand what's usually just a chaotic mess of electrical noise in the brain. We'll look at how this helps researchers, helps developers too, and how it even helps us understand those ghosts in the machine, the annoying interference that messes up real recordings.
Okay, right, let's unpack that. So EEG, at its most basic, what actually is it? For anyone maybe not swimming in neuroscience daily, it's a way, a non-invasive way, to record the electrical chatter from big groups of neurons firing together. Brainwaves, basically. And these signals, they give us these incredibly valuable real-time insights into everything from how focused you are to spotting neurological issues. But here's where it gets really interesting, almost like conducting a digital orchestra.
Exactly. So the thing we're focusing on today is the Advanced EEG Signal Simulator. It's a web-based tool, and it's specifically designed to generate synthetic EEG signals. Think of it like a really carefully crafted artificial waveform. It's designed to perfectly mimic real brain activity, combines those fundamental brain waves we know, the slow delta waves of deep sleep, theta for drowsiness or meditation, alpha for relaxed wakefulness, and the faster beta waves for when you're alert and thinking hard. And, this is key, it lets you deliberately add in common sources of noise, what we call artifacts.
So it's like this digital sandbox where you're the puppet master dialing up focused or dreaming just by clicking around. That sounds, incredibly powerful.
It really is. You can literally fiddle with controls and watch the waveforms change right there on the screen. Imagine teaching, right? Instead of just static pictures, you could select, say, relaxed meditative from a menu, and boom, you instantly see this strong alpha waves pattern appear, just like you'd expect. Or you could tweak individual wave settings, like amplitude or bandwidth, showing exactly how tiny changes affect the whole picture.
Okay, but why? Why would you need a fake brain signal when you've got a perfectly good, if messy one, running in your head right now? It feels a bit counterintuitive, doesn't it? Like building a simulation of a car to test how a real road works.
Yeah, that's a really important question. Why synthetic? And the answer, it covers a few critical areas. First, learning and education, it's just invaluable. Students can get an intuitive feel for how different brain states look, how waves combine. And they can do it without needing all the complex, expensive, often kind of finicky, real EEG gear. But maybe even more importantly, it's vital for algorithm development. Think about engineers, data scientists building tools for, say, brain-computer interfaces, or maybe new ways to spot signs of epilepsy. They need a reliable, predictable signal to test their code against real EEG. It's all over the place. So the simulator simplifies things. It gives them a clean baseline, helps them build and test their tools, especially the ones meant to remove those artifacts we mentioned.
Right, artifacts. Speaking of chaos, real brain recordings are never as clean as those perfect sine waves you see in textbooks, are they? They're always contaminated by these artifacts. It really is like trying to hear a whisper during a rock concert or, understanding someone across a really noisy bar. What are these things, these noisy gate crashers?
Well, in the real world, outside the lab, EEG recordings are just constantly getting contaminated by electrical signals that aren't from the brain. They come from your own body, but not your brain cells firing. And the simulator is smart because it lets you add in two of the biggest culprits. First, there's muscle artifacts, EMG. That's high-frequency noise from simple things like clenching your jaw or frowning, maybe even just tensing your neck muscles. And then you've got eye blink artifacts, EOG. These show up as these big, slow-wave spikes when you blink. Pretty obvious one, that.
So, wait. Your own body is basically sabotaging the readings of your brain. That's actually darkly funny, isn't it?
Yeah.
The ultimate kind of self-inflicted wound in science. I remember reading somewhere that eye blinks are often called the most dominant unwanted signal in EEG. And they can actually mess with your theta and alpha rhythms, especially right at the front of the brain where lots of thinking happens.
Oh, absolutely. It's a huge problem. Imagine you're trying to get a clear read on someone's cognitive state, but every single blink throws this massive electrical spike that just obscures everything. It's a real challenge. And yeah, another study highlighted how big a deal muscle artifacts are, especially during sleep studies. They found it can make up like 20 to even 70% of the total signal power in those higher frequency ranges, say 15 to 32 hertz. So being able to spot and filter out these transient non-brain signals is just critical if you want to interpret the actual brain activity correctly.
Okay, so this is where the irony kicks in, right? We developed these amazing tools to create perfect synthetic brain signals, clean, predictable. But then reality is so messy that we actually have to make our fake signals messy as well, just so they're useful. That's just a brilliant, almost tragicomic twist in how science works.
It is, isn't it? A fascinating paradox. And the YouTube deep dive on this specific simulator points out something really important about that. The underlying Python code. It actually generates a random frequency within the specified range for each brainwave band every time you run it. So even if you use the exact same settings twice, the output signal will be slightly different. Now, this isn't a mistake. It's deliberate. This random variability makes the synthetic data much more like the natural, subtle fluctuations you always see in real EEG. Because think about it. If your fancy new algorithm only works on perfectly clean, unchanging waves...
It's going to fall apart the second it sees real data.
Exactly. It just won't survive contact with a real, messy, beautifully complex human brain signal. It needs to be stress tested on something closer to that reality.
Okay, this leads us to a really fundamental point then. If real brain data is just naturally full of noise and randomness from our own muscles blinking to the basic physics of the signal itself, how do we even know what's real brain activity versus just, background static? What does this mean for how we've traditionally looked at brainwaves? For decades even.
This is probably one of the biggest shifts happening in how we understand EEG right now. The main challenge is that the power spectrum of an EEG signal, how much power there is at different frequencies, typically has this one F-like decay. What that means is you generally have lower power at higher frequencies. Think of it like a constant underlying hum or broadband noise that's just always there, kind of like static between radio stations. And the sources we looked at, especially that Sapien Labs paper, they show that the field historically has basically confused this background noise with genuine, distinct brain oscillations. Early researchers, they didn't have the computers we have now. They had to simplify. So they just started dividing the whole spectrum into these broad bands, like alpha waves here, beta waves there. And they kind of assumed everything within that band was one specific pure wave.
Whoa. So we've been calling these broad chunks of activity waves like the alpha wave for relaxation, beta for focus. But a lot of that might actually just be this background hum, this non-periodic noise. That feels like a huge misunderstanding that's been hiding in plain sight. A fundamental assumption that might be, wrong. Does that mean, countless studies might need a second look?
It's a pretty profound realization, yeah.
Yeah.
The Sapien Labs paper really drives this home. It argues that traditional measures, like just measuring the total alpha power in that band, are often reflecting changes in that overall 1F background hum more than changes in a specific emergent rhythmic component. So what does that mean? It means a reported change in alpha power could just be because that background noise level shifted slightly. It might have nothing to do with a true change in actual brain oscillations.
Yeah.
And that has massive implications for how we've interpreted everything from brain states and cognition to neurological disorders. It definitely suggests that a lot of past findings might be looking at, maybe not the wrong thing, but misinterpreting where the signal change is coming from.
Okay, so if the old way is potentially flawed, how do we find the real signal, the actual rhythmic activity hidden in all that background noise? It sounds like we need a much smarter way to listen, something that can tune out the static.
We absolutely do. And that Sapien Labs paper proposes exactly that. A new metric they call oscillation energy, or E0, sometimes written E specifically for the alpha band. It's designed specifically to separate the true oscillatory peaks, the actual waves, from that pervasive, non-periodic background noise. Now, the method is a bit technical, involves things like autocorrelation, FFT, a second-order differential. But without getting lost in the math, think of it like a really sophisticated filter. It's designed to amplify the detection of those small, genuine oscillatory signals, making them pop out from the background hum. The beauty of it is that it's much less sensitive to those overall shifts in the 1F background noise. It's like turning down the static on the radio so you can hear the actual music underneath more clearly.
Now, that is fascinating. They tested this, right? What did they find when they compared Eeyore to the old alpha power measures? Because the classic finding is alpha goes up when you close your eyes. That's like EEG 101.
Exactly, and that's what they checked. They found that EEA consistently, reliably increased when people closed their eyes. Just as expected, right? Stronger alpha oscillations. But the traditional alpha power measures, all over the map. Sometimes they went up, sometimes they barely changed, sometimes they even decreased. And crucially, there was very little correlation between the traditional alpha power and this new EEA measure.
Wow. So it's like getting two totally different readings for the same basic phenomenon.
Yeah.
That really underscores the potential problem with the old methods.
It really does. That stark difference shows how misleading the traditional metrics can sometimes be. Easier, or EEA, seems to provide a much more precise, much more sensitive measure of the actual periodicity, the real rhythm. It's almost like a signal-to-noise ratio specifically tuned for the brain's internal rhythms. And another bonus, it's also significantly less bothered by those eye blink artifacts contaminating the alpha band. Why? Because it focuses on finding local differences in the power spectra, those sharp periodic peaks, rather than trying to fit a smooth curve to the entire noisy signal, background hum and all. So you get a much cleaner, arguably more accurate picture of what the brain's really doing rhythmically.
Okay, so we've got these incredible simulators now. They help us learn, they help us test algorithms, they even let us build these digital doppelgangers of brain states. And now we also have these smarter ways, like, to analyze the real signals hidden within all the noise. So looking ahead, what's next? What does the future hold for designing these digital brains and using them to better understand our actual organic ones?
Well, the advanced EEG signal simulator itself has a roadmap. They're planning to add more complex waveforms, like gamma waves, which are linked to higher-level cognitive stuff. And continuing our little theme of irony here, they're planning to add even more types of artifacts. Things like EKG, the electrical signal from the heartbeat, which can definitely show up on scalp EEG. And even that infamous 50 or 60 hertz power line noise, the static hum from your electrical outlets finding its way into your brain data. It comes back to that idea. To make a simulator truly useful, it needs to be almost as messy and inconvenient as reality itself.
More noise. You weren't kidding. So the quest for the perfect synthetic data actually means making it as realistically flawed as possible. It's this beautifully perverse cycle, isn't it? Build something perfectly clean, then meticulously add all the real-world imperfections back in.
Exactly. And it's not just this one tool either. There are other simulators emerging, often open source, like Unfold SimJL. These are offering even more complex simulations, things like multi-channel support simulating data from many electrodes at once, and even more realistic types of noise. And look, these aren't just academic toys for people to play with. They're becoming essential, critical tools. They let researchers rigorously test and validate the algorithms that could, one day power really advanced brain-computer interfaces. Think communication for locked-in patients or controlling prosthetics. Or they could lead to much better diagnostic tools for conditions like epilepsy or maybe even Alzheimer's disease. These simulators help accelerate that kind of discovery.
And for people who want to dive into real brain data, warts and all, even with all its glorious chaos, there are resources out there too, right? Like open data repositories.
Oh, absolutely. There are some fantastic open source repositories now. Places like the OpenBCI community website, OpenNeuro is a big one, the NMT Scalp EEG dataset. These platforms host huge amounts of real human EEG data that researchers, students, or even just curious individuals can access and analyze. So yeah, the brain in all its messy, complex, rhythmic glory, it's becoming more accessible for study than ever before, both in its raw biological form and through these increasingly sophisticated digital copies.
So we've taken quite the journey today, a deep dive into this surprisingly complex world of simulating brain waves and analyzing the signals. From creating these perfectly clean digital brain states to then painstakingly recreating all the biological noise that makes reality so tricky. It seems pretty clear that understanding the fake really does help us understand the real. It's been critical, definitely fun, and profoundly ironic too.
Absolutely. And maybe if we connect this back out to the bigger picture, it raises a really interesting question for you, the listener, to think about. How does this constant dance, this back and forth between creating controlled, perfect simulations on one hand, and then deliberately grappling with messy, noisy reality on the other, how does that change how we should approach any complex biological system? When we build these incredibly precise digital copies, what important details, what vital nuances might we risk overlooking in the real thing? And conversely, what unexpected truths, what critical insights do we perhaps only stumble upon when we fully embrace the imperfections, the noise, and the beautiful chaos of reality itself?
Yeah, okay, there's a human in the loop. If you have any questions, go for it.